Hello AP, this is Mrs. Sargent, and this is sections 13.3 and 13.4 in your book. We're going to look at equilibrium expressions involving pressures and heterogeneous equilibria. So to start with, we have the equilibrium expressions involving pressure. Pressures can be used in equilibrium expressions, and the equilibrium constant is called Kp. So instead of it being called Kc or Kaq, it's just Kp, denoting that it is pressures. Using the same mass action equation as above, the Kp expression becomes P, the partial pressure at equilibrium, but it has to be in atmospheres. So all you're going to do is you're going to plug in the pressure for each of your species in your equation, raise it to the power of the coefficient to solve for Kp. Another way to solve for Kp is using the Kc with the concentrations and looking at the change in moles. So Kc involves concentrations while Kp involves pressures. Kp and Kc can be interconverted using the following relationship. So Kc is equal to Kp if the number of moles of gaseous product is equal to the moles of gaseous reactant. So what this is saying is if in the products you have 2 moles of products and in the reactants you have 2 moles of reactants, then your Kp is just equal to the Kc. However, if it is not equal to each other, then you would need to use this equation. So Kp is equal to Kc times the gas constant R, so not the 8.314 that we've been using, but the 0.08206 liters times atmospheres per mole times Kelvin, times your temperature in Kelvin, times or raised to the power of the change in your moles. So you're going to take the number of moles of gaseous product minus the number of moles of gaseous reactant. So the meaning of the equilibrium constant. And we're going to continue to talk about this. But a value of K that is greater than 1 means that the equilibrium is far to the right. So this is going to form mostly products. So anytime you see a very large K, the reaction is going to completion. And it has more products than it has reactants. A value of K that is less than 1 means the equilibrium is far to the left and mostly reactants. So the reaction is hardly going at all. The size of K and the time needed to reach equilibrium are not necessarily directly related. K values cannot always be directly compared because the stoichiometry differs. So let's take a look at this example. It says, consider a reaction of 2 NaCl forming 2 NO and 1 chlorine at 35 degrees Celsius. So when 3 moles of NaCl and 1 mole of NO and 2 moles of chlorine gas are all mixed in a 10-liter flask. After the system has reached equilibrium, the concentrations are observed to be as follows. Now, you might be looking at the 3 moles in the 10-liter flask and be thinking about calculating your molarity based off of that. But the K value is at equilibrium. I apologize. My dog just decided she wants to play with her toys right now. So if you hear that, I apologize for that. You're going to calculate the value for K for the system at 35 degrees Celsius. So let's first write our equilibrium expression. So K is equal to the concentration of NO and the 2 coefficient. We're going to square that. And then chlorine We only have one of those. And then our NaCl, our reactant. And we have 2 moles of that. So that is also going to be squared. So now what we're going to do is we're going to plug in these equilibrium concentrations to solve for K for this system. So we're going to take K is equal to the concentration of NO, which is 4.00 times 10 to the negative third molar, square that, multiplied by the concentration of chlorine, which is 1.52 times 10 to the negative first, divided by the concentration of NaCl, which is 3.96 times 10 to the negative first. And we have 2 moles of that reactant. So when we solve for this, we are going to find the K value to be 1.55 times 10 to the negative fifth. So now we're going to use this K value as we look at some other scenarios with this same equation. So the first scenario, we're looking at the reverse of the equation. So we're looking at the NO and the chlorine being the reactants and the 2NOCl. So if you remember, this is K prime from 13.2 notes, and so that is going to be 1 over K. So we're going to do 1 over our 1.55 times 10 to the negative fifth. And when we calculate that, we should get 64,516. Of course, we want to round that to 3 sig figs, so 64,500. Or you can put it into scientific notation, 6.45 times 10 to the fourth. Either way is fine. Now, part C says calculate the value for K for the reaction of 4NOCl, 4NO, and 2Cl2. Now, we're back to that original equation. So the NOCl is our reactant, NO and chlorine is our products, but now we're looking at 2 times the original concentration. So this would be K prime. And so whenever you have your original reaction, just doubling the coefficients, you're going to square that. If it was 3 times the coefficients, it would be cubed, and so on. So now we're going to do 1.55 times 10 to the negative fifth, and we're going to square that. And that is going to give us 2.40 times 10 to the negative 10th. And then our last example with this same equation, we're looking for Kp of the first reaction. Now, we aren't given any pressures in this problem, so we're going to be using the equation Kp is equal to Kc times the gas constant times our temperature in Kelvin raised to the power of our change in moles. So let's look at our change in moles to begin with. So we have 3 moles of products, 2 moles of NO, 1 mole of Cl2, and 2 moles of reactants. So 3 minus 2 is equal to 1. So now for Kp, we are going to take our Kc, our 1.55, times 10 to the negative fifth, and then we're going to multiply this by our 0.08206 liters times atmospheres per mole times Kelvin. Multiply that by our temperature, which 35 degrees Celsius plus 273 is going to give us 308 Kelvin. And our number of moles is 1, so raise it to the 1. So Kp is going to be equal to 3.92 times 10 to the negative 4th. So that is it for section 13.3 and 13.4. We're going to start looking at the application of the equilibrium constant next. Thanks. Have a great day.